Hello, students. Today we're going to solve this problem having to do with compound interest. The problem is basically looking for a value of n in the compound interest formula, which is the number of compounding periods, such that the amount in the account is at least tripled over a 20-year period. So we're going to be using the compound interest formula, which is the amount is equal to the principal, there's a P in there, times 1 plus the rate expressed as a decimal over the compounding periods, the number of compounding periods, raised to the power of the number of compounding periods times the time interval that the compounding periods are relevant to. In this case, we have years, so n is the number of compounding periods in a year. We're also going to be using a methodology for solving this problem called binary search. It's also sometimes called a half interval search. It's used when you get sort of a hairy mathematical situation, which you get. If you try to solve this problem for n, you're going to get into some interesting math that it's not really necessary to solve a problem that is this simple if we use an efficient technique like this called a binary search. For simplicity, I'm going to set P is equal to 1. No point in making anything else. We just know that we want to get 3 times that. So basically the problem we're trying to solve is that 3 is less than or equal to 1 plus 0.055 over n to the power of the number of years times the intervals. 20 times n is the same as n times 20. Okay, so let's set, for the first round, let's set n equal 1. Let's just try that out. Put that into your phone calculator, and this part right here is A. If you do that, you're going to get A is equal to approximately 2.9178. Let's try n equals 20. I'm sorry. Let's try n equals 10. Let's go back. Try n equals 10. Put that into your calculator. You're going to get A is equal to approximately 2.995. Okay. Let's try n is equal to 20. You're going to get A is approximately equal to, at least in my calculator, A is approximately equal to 2.999, and it goes on. Let's try n equals 30. And we're going to get, lo and behold, in this case, all of a sudden now, A has broken 3. We're now over the value of 3, which was our target. So it doesn't much matter how much over 3 it is. We know that n equals 30 does the job. Now, the binary search methodology says, let's half the distance between the two searches that produced values that bracket the target that we're looking for. So half the distance between 20 and 30 is 25. Let's try n equals 25. And you get A is approximately equal to, and still over 3, which is great. All right, you have to go out a couple more decimal points to get it. So now we have got the two values for n that bracket our target are 20 and 25. So what's half of the distance between 20 and 25? Well, it's 2.5. Well, we can't get a half of an interval. So let's just try n is equal to 22. then you're going to get A is equal to approximately, well, it goes way out. Still over 3, so forth and so on. Well, let's try n is equal to 21. See what happens. Now you're going to discover that A has dropped back down below 3. 2.999. How many 9s do I have? And so forth. So we know that n, if this was simply a mathematical problem, would be somewhere between 21 and 22. But since this is a real world problem, we want a number of intervals, which is an integral number. So our answer in this case, since this has to be greater than or equal to 3, the answer is 22. Okay. I hope you enjoyed this and hope you learned something. I'm Jim Richards, and I'm happy to be here on the Wyzant website talking to you.